Hello, today we're going to be looking at problem 743, network delay time. So you are given a network of n nodes labeled from 1 to n. You are also given times, a list of travel times as directed edges, where u is the source node, v is the target node, and w is the time it takes for a signal to travel from its source to its target. We will send a signal from a given node k. We want to return the minimum time it takes for all the nodes to receive the signal. If it's impossible for all the n nodes to receive the signal, we'll return -1. So let's look at an example here. We have n equals 4, so there's 4 nodes in our graph, and k equals 1. So we're going to start at node 1. And let's not think of any algorithms right now. Let's just look at how the signal might travel. So we're starting at 1, and maybe we first travel to 2. This takes 1 second. From 2, we travel to 3, which takes 3 seconds. And then from 3, we travel to 4, which takes another second. So the network delay, if we took this path, would be 1 plus 3 plus 1, which is 5. So it would take 5 seconds for the signal to take this path. We can see just from looking at this graph, this is not the fastest way for the network to reach all of the nodes. This here would be the fastest way because 4 is our farthest node, and to 4 it takes 1 second for the signal to get from 1 to 3, and then another second for the signal to get from 3 to 4. So our longest path is 1 plus 1, which is 2. So we're going to choose a breadth first search algorithm for this problem because we want to find the minimum time it takes to traverse to all of the nodes. And we just want to watch out for one little tricky thing in our problem. So usually when you look at a more complicated example, it might expose parts of the problem that are hard to find in these really small, simple examples that LeetCode gives us. So let's look at one with an extra node. We have node 5 here. So if we do a breadth first search, again, we're going to start at 1. First, we're going to visit 3. Then we're going to visit 2. Then, since it's breadth first, we would go back to 3 and look at its edge to 5, and so on. Eventually, we would get to this edge here where we see 4 connects to 3. And we can see in this graph that the fastest way to get to 3 is actually from going from 1 to 2 to 4 and then to 3. That takes only 4 seconds, whereas going from 1 to 3 takes 5 seconds. So yeah, usually in a breadth first search, we don't want to visit nodes more than once. We often have a set of nodes we visited and we check on that set, and if we've already seen a node, we don't want to look at it again. But in our case, we actually do want to look at nodes a second time. And this is because of cases like this one where to get to 5, the shortest path is going to take us 5 seconds here rather than 6 seconds if we just go from 1 to 3 to 5. So now let's talk about our algorithm. The first thing we're going to do is create an adjacency list of each of our nodes and its connections. Then we're going to create an array of the minimum visit time to each node. We're going to push our node k onto our queue, and then we're going to go through our queue. So while our queue has nodes, we want to pop a node off of the queue. This will be the current node. For each of its adjacent nodes, we want to check if the minimum time to visit from the current node is less than its existing minimum visit time. And if it is, then we want to push that adjacent node onto the queue. After we've done all of this, we want to find the maximum visit time for all of our nodes. Now let's see our algorithm in action with that original graph that we looked at. So first, we're creating our adjacency list. So this is a list of our nodes and all of the edges that they have. So we can see here that 1 has a edge from 2 to 1, and that takes 1 second. And it also has an edge from 1 to 3, which also takes 1 second. So we're doing that for each of our nodes. Then we're going to create our minimum visit time array. So this is the minimum time it takes for the signal to reach each of our nodes. And I'm going to initialize this to -1 for all of my nodes, meaning that I've never actually visited them. And then I'm going to set the node k to be 0. So our first element is going to be 0. Then we have our queue, which is empty. So let's push our first node onto the queue. So we pop that node off, and now we would be in our looping portion. So we look at our adjacency list, and we look at the first edge is to 2, and that takes 1 second. So let's look at our minimum visit time and see that it's currently -1 because we've never visited 2 before. So we're going to update that to be 1. Now our second edge, again, see that 3 has never been visited, so we're going to update that to 1 as well. And we're pushing these onto the queue because we updated their minimum visit time. Next, let's pop 2 off of the queue. Let's look at its adjacent nodes. So first we have one from 2 to 3. And currently the minimum visit time from to 3 is 1. So we compare, is 3 plus 1 less than 1? No, it's not, so we're not going to update that, and we're not going to push it onto the queue either. Next, we look at our edge which takes 2 seconds. Again, we see this has never been updated, so we update it to 3. And we want to remember that we're updating this to the time to the current node plus the time to the adjacent node. So this is going to be 1 plus 2. And we're going to push that onto the queue. Then we go from 3 to 4. We see that 1 plus 1 is less than 3, so we're going to update that to be 2. And that's pretty much it for our algorithm. Once we reach 4, that doesn't have any adjacent edges, so we wouldn't do anything for it. The last thing we want to do is we want to look at our minimum visit times and see which one is the largest. So clearly we can see 2 is the largest here. So we select 2 as our return value because that is the longest signal. Now let's look at the code quickly. So I wrote this in Java. So the first thing I do is I create an adjacency list of each node and its connections. So I create an array list, and this contains a list inside of it, and I'm going to store my adjacency list in an integer array with just 2 elements in it. So we're going to go through our input object here, which is times. And for each value in this array, it contains an inner array, so that has the source node, the destination node, and the time. We're going to see if this already exists in our list, in our adjacency list. And if it does, we just want to add onto it. So we're going to create our neighbor node, which is our adjacency list. So like I said, that just has two elements. It has a destination node and the time it takes to reach that node. And we're going to add it back into our adjacency list. The second thing we're going to do is we're going to create an array of minimum visit times to each node. So I create minimum visit time and I just fill it with -1s, and then I set k equal to 0. So that's where the signal starts. So we're always going to be 0. We're going to create our queue and we're going to add k to it. And while the queue has nodes, we're going to iterate through it. So the first thing we're going to do is we're going to pop the head off of the queue. And then for each of its adjacent nodes, we're going to check if the minimum time to visit from the current node is less than its existing minimum visit time. So the time to the current node is the minimum visit time of that node. And then we're going to get all of its neighbors. If it's null, we're just going to skip over it. If it's not null, then we're going to go through each of its neighbors. So we're going to see the destination node and the time to that destination node. So if the node has never been visited, we know we want to update it with the current signal time. Or if the time to the current node plus the time to the destination node is less than the current minimum time, then we also want to update it. So we're going to update it here, and then we're going to add it to the queue. And now we're exiting out of our loop, and we want to find the maximum visit time from all nodes. So we're setting it originally to -1, and then we're going to look at the visit time from each node. So this is an important part that I didn't talk about in my algorithm, but if we've never visited a node, we're going to see that the minimum visit time will be -1, and it told us in the instructions that if a node isn't visited, or it says if it's impossible for a node to receive a signal, then we return -1. So if we see a -1 in our visit time array, then we automatically want to return -1. Otherwise, we update the maximum and return that. And we can see that we'll submit that, and it did submit. Last thing I want to talk about is the time complexity. So we want to remember that we visited all of our nodes once, and for each node we visited all of its edges and potentially went back to nodes again. So you might think, what if we have a graph like this one where we only have an edge from 1 to 2 and from 3 to 4? So we have two graphs that aren't connected to each other. In this case, we want to remember that time complexity is measured by the worst possible input. So the worst possible input would be something like this, where the graph is connected to every single node, and we could possibly traverse each of the elements e number of times if the graph makes us come back to our nodes. So that means the time complexity is O(n) times e.